Okay, we're going to start the review of equilibrium. So this will be the equilibrium So, first thing to really answer is, what is equilibrium? Okay. And to do that, let's take a step back for a second and just kind of look at kinetic energy and a liquid. Okay. If I have a sample of liquid and I leave it out in the air, all right, this sample of water, and we're going to use water, okay, at a temperature, okay, we can look at the kinetic energy of that sample looking at a Maxwell-Boltzmann again, and being careful not to draw that into the line. And from here, if some particles are going to have enough kinetic energy to escape into the vapor phase. Okay. And if I have this open system, those particles are going to escape, okay, and over, I guess, a course of a couple of days, depending on the temperature, all the water will evaporate into the system, right? However, if I take that same system and I close it off, so I have a closed system, okay, I'm still going to have particles that have enough energy to escape into the system, into the vapor phase, but some of those particles in the vapor phase are going to be low in energy, that when they collide with that surface, their kinetic energy isn't enough to overcome the intermolecular forces, and they're going to go back into the liquid phase. Remember that the closed system is something that doesn't exchange matter or energy with the surroundings. Okay. So the idea in keeping that Boltzmann diagram in mind, some particles have enough energy to escape into the vapor phase. Some of those particles in the vapor phase have low enough energy that they're going to come back into the liquid. Okay. Eventually, the number of particles going up is going to equal the number of particles going back into the vapor phase. So the number of particles going into the vapor phase is going to equal the number coming back down into the liquid phase. I think I said that wrong the first time. All right, and this is really an example of a dynamic equilibrium. I do still have movement of particles, but the rates are the same. The number going up into the vapor phase equals the number coming down into the liquid. Okay. Okay, let's look at a favorite system of the IB, and now we're going to switch kind of into chemical equilibrium. Okay, and this is the Haber process. Okay, where I have nitrogen gas reacting with hydrogen gas to form ammonia gas. All right, and remember, for a chemical equilibrium, the rate forward is equal to the rate in reverse. If I were to look at an equilibrium over time and look at the concentration of, say, nitrogen and the concentration of, say, hydrogen, and purple, concentration of NH3. What I will see, say nitrogen starts off up here and it reacts, and then hydrogen, because it's 3 to 1 for hydrogen, say it starts here, it's going to have a 3 times the curve. Okay, so as those reactants are being used up, then my, I don't know what, I was doing something weird. Okay, then my ammonia will be produced. So the ratio there should be the change for one nitrogen should be like 3 times for the hydrogen and then twice for the NH3. All right, so the curve should reflect relative distances shown in the equation. All right, so say at a particular point in time in this graph, say I make a change to the nitrogen and I add some to my system. Nitrogen then will react. Okay. It's going to react with some hydrogen. I didn't draw enough, that should be 3 times that curve. And I'm going to be making more. This should be twice the curve. Oh, gosh. Okay. And then I will make a new equilibrium, but once I reach equilibrium, then those concentrations of those different things remain the same. I hope that that makes sense. Okay. When working with an equilibrium system, we use something called the equilibrium constant. Okay. And generally, it is going to be the concentration of the products over the concentration of the reactants. And remember, you're going to raise them to whatever the stoichiometric coefficient is. So as an example, if I have A reacting with B in equilibrium with C and D, my equilibrium constant is going to be the concentration of C to the C power, D to the D power, A to the A power, and B to the B power. Okay. This, the equilibrium constant is constant at a given temperature. Okay. So if I disturb my equilibrium system, keeping the temperature constant, the concentrations of the reactants and products are going to shift and change to maintain that equilibrium constant. Okay. Let's take a look at the magnitude of Kc. Okay. If the magnitude of Kc is much greater than 1, the reaction is said to go to completion. Okay, really meaning I have way more product than reactants. And for example, if I look at zinc reacting with a solution of copper ions, it will set up a equilibrium kind of where I get zinc in solution and copper solid. The Kc for this is 1 times 10 to the 37th. That's pretty big, and that's at 298 K. All right, and this is really said to be going to completion. Okay, conversely, if Kc is much less than 1, there is no appreciable product formed. And I have almost all reactant. Right? Then if Kc is about equal to 1, then I will have both reactants and products. Reactants and products in my system. Okay. Okay. Le Chatelier's principle. Okay. This states if a dynamic is disturbed by changing the conditions, the position of the equilibrium moves to counteract the change. Okay, and everything but a change in temperature, your equilibrium constant will remain the same. So the equilibrium is going to shift to change the concentrations of reactants and products to get back to that equilibrium constant. Okay, so change of pressure on a gas system, assuming that this is a volume change, okay, will shift to the side with less moles of, I'm writing swift, it's shift, oh geez, oh geez, shift, oh, I'll get there, hang on. Okay, an increase in pressure will cause a shift to the side with less moles of gas. Okay. Note, addition of an inert gas, there is no change because you don't change the concentration of the gases there. The partial pressures do not change. So addition of inert gas, no change. Okay. Change of temperature to a system. Okay. This changes your Kc. Okay. If temperature increases, okay, and it is an exothermic reaction, the equilibrium will shift to reactant side. Okay, so really what you do for a change in temperature is you add heat as a product for an exothermic or as a reactant for a endothermic. Okay. And you're going to treat that, and I guess you know what I didn't do. Like say we have A plus B going to C if I add heat. Okay. So if I add heat, it's going to shift this way to minimize the heat added kind of thing. One thing that I didn't talk about, and I probably should have, is if concentrations. Okay, if I were to decrease the concentration of C, the shift will be to make more of C. Okay, and I hope hopefully that kind of thing is coming back to you. All right. We'll pick up on the Haber process and the contact process for the next screencast.